Alright guys, you're welcome to another training module on the analysis of beam structure, right? And in this module, I'll just be taking you through analysis of statically indeterminate structures, right? So the ones we've been having earlier on, they are on statically determinate structures. So about this, to identify statically indeterminate structures, when we have the number of forces exceeding the number of the three equilibrium equations. Of course, by now we should know what the three equilibrium equations are. We know that the sum of vertical forces must be equals to 0, and the sum of horizontal forces must be equals to 0, and the sum of the moments must be equals to 0. So these are the three equations of static equilibrium. Right, so if the number of forces exceeds these three numbers of equation, we term the beam as a statically indeterminate beam, or any structure, be it as it may. Right, so the number of forces we have here, right, we have one vertical force here, we have the second one here, we have the third one here, and we have the last one, 4. Right, so the number of forces here is 4. Then the number of statically determinate equations, or static equilibrium equations, number of equations is 3. So for you to know the degree of indeterminacy, so let me take this off. For the degree of indeterminacy now, you just subtract the number of forces, the three equilibrium equations from the number of forces, then you have 1. So this is indeterminate to the first degree, right? So this is not actually the big deal. The big deal is how to analyze this beam element so that we can obtain our span moment and support moment, and from there you can have um, your design appropriately, right? So from here now we want to actually go on into analysis. There are several methods that, by which we can actually analyze indeterminate structures, but in this module I'll be taking you through the moment distribution. And of all these methods, we have the first method. Now let me just outline them properly. We have the first method, the flexibility method, then we have the moment distribution now. Method of analyzing indeterminate structures. The first method, we have the flexibility method, as said. Then we have the moment distribution method. And this moment distribution method is otherwise known as the Adicross method. Adicross method. Right, even before now, many of us had made contact with several methods like the three moment equation and the slope deflection method. Right, these are methods also under this listed. So but for today we are going to place our focus on the moment distribution method. Right, this actually affords us of short processes and steps to have our moments obtained, right? Unlike the slope deflection equation, where you have multiple equations which will probably lead to simultaneous equation and may have challenges analyzing along the way, and it becomes too long. But moment distribution can help you achieve those things in simple steps. So right now, let's take a simple example. Like I have this beam structure, a three span beam that we have here being loaded by varying loads, 4 kilonewton on the first span, kilonewton per meter, and second span we have 30 kilonewton per meter, and the third span we have 25 kilonewton per meter, right? So there are basic steps to obtaining your results with moment distribution, right? So the first thing I'd like you to know is there are basic assumptions to using moment distribution. Basic assumptions, right? So the first assumption, let's just put them down, and at the end of this module is expected that you get all that you need to get about moment distribution accurately. So we have assumptions. The first assumption is that all joints are rigid. All joints are rigid. All joints are rigid, right? So the second assumption will mean that the displacement due to axial and shear stress, they are very small and negligible, right? So deflection due to the axial and shear stresses are small, and thereby you can neglect them, so they are negligible, right? So these two assumptions, they are enough for us to proceed to analyze our beams. So another thing I'd like to show you is the sign convention, of which in the previous module you guys are familiar with sign convention. All right, so is sign conventions, which you might customize one for your analysis. So but for me, I'm convenient using my positive movement, positive movement to be clockwise, right, and my negative movement to be anti-clockwise, right, anti-clockwise. So but for other guys, you might choose to use whatever suits you, as long as you are consistent in the application, right? So moving on, we have another thing you should pay attention to, which is our stiffness, member stiffness. Let's call it the member stiffness. Member stiffness. So the member stiffness is denoted as K, right? So to obtain this, you need to pay attention to the end condition of your span. You know, the assumption says that all our joints are rigid and unmovable, so to say, such that they are fixed. All our joints are fixed, but we would want to pay attention to our end support, because sometimes, most times, it defines what expression we give to our stiffness in application, right? So we just want to paint one or two things, and we'll give explanation to them simply in this tutorial. So assuming we have a span, we have this first span 1. Let's call this span 1. We call this span 2. Then we call this span 3. Right? So taking out span 1, this outer support is taken as simply supported, right? So we take it as simply supported. Then then we take these as fixed, having told us that our joints are fixed, so we have this as fixed. So being fixed, we have moments around that place, and we have vertical forces, the vertical force and the horizontal force. Of course, we know that already. And we have this span in application, right? So for this particular arrangement, seeing that we have the end support as simply supported, right, is pinned right now in application. So the stiffness factor here will be taken as 3E high over L. So each time your end support This is now the far support. Let's take this as A and B. So the far end of B is simply supported. So we have the value of K to be 3E high over L, right? So if we have in application another situation where the support, the end support, the outer support right now is fixed. So we are considering span 2. Considering span 2 here, right? This is fixed. This is fixed. So we have the moment in application, right? We have the force and the force. Now, these two ends are fixed, and it signifies or indicates that the stiffness factor will be 4EI over L. Right, so that's simple. So we have a summary from the stiffness expressions that we have just showed ourselves right now, that for fixed support, when your end support is fixed, the stiffness factor will be 4EI over L. When the end support is simply supported, we have the stiffness factor to be 3E high over L, right? So you need to pay attention to this, because once you get this all wrong, it affects your analysis, right? So from here we can actually proceed to obtaining our distribution factor, right? So you just want to pay attention to all these steps that I've been outlining, then we'll be able to achieve results with them, right? So for distribution factors, let's see if I can use one of these slides. Okay, so for distribution factors, for distribution factors. So, for example, distribution factor for any point or row and column, of which I will explain, will be equals to the stiffness of that in question and summation of the stiffness. Right. So, for example, we are considering a 3-span beam. All right. So we have A, B, C, and D. Right. So if we have stiffness for BA to be 3E high over L, and your answer obtained was 0.22, then you have stiffness for BC to be 4AI over L. We should know the reason why it is like that. Then we have 0.24. I do not know, but these are educated guess actually. I'm trying to explain the distribution factor to you. So if we are supposed to get the distribution factor for BA, so that will be the stiffness for BA itself divided by the summation of stiffness at that point, which means KBA plus KBC. So that will be 0.22 divided by 0.22 plus 0.24. That's exactly what I'm saying, right? So if we're going to apply this correctly, that's supposed to give you that's supposed to give you an answer, which when you subtract from one, you pardon me, you have that for the other end, right? So we have 0.48 for this, 0.48, right? So for distribution factor of BC, right now, if you're going to apply that, that will be KBC divided by the summation of K at that joint, right? So we have 0.24, which is that for KBC divided by the summation of stiffness at that point. So that will give 0.52. Right, so this is how you know whether you're correct or not. The summation of your distribution factor at any joint should be equals to 1. Right, so adding these two guys together, we have 0.48 plus 0.52, then is equals to 1.0. Now, this is these are important stuffs that we are going to be applying in our iteration, because moment distribution has to do with iteration. If you understand these basic things I've shown to you, you can actually flow along with every other thing that I'll be telling to you. Right, as a way of reminder, can we just see that from here we have the statically indeterminate structure, which is a product of the fact that the number of forces acting on a beam exceed the numbers of the equilibrium equations, right? The three equilibrium equations. So we have four forces acting upon the beam, and the number of static equilibrium equation, there are three. So we have this kind of beam element statically indeterminate to 1 to the first degree. Right, I told us of the method of analyzing indeterminate structures. We have them already, and also we have assumptions for um, taking the moment distribution method. All joints are regarded as fixed or rigid, right? And the deflections are small and negligible, right? So for the sign convention, we spoke about that, and I'm assuming this, which you might assume the other direction, but the thing is you have to be consistent in your application, right? On the member stiffness, I told you once your end support is simply supported, the stiffness is going to be K is equals to 3E high over L, and when the head support is fixed, your stiffness remains 4E high over L. Now to go straight forward to distribution factor, I explained to you all through about this, and you should get that as simple as possible right now. So let's have so now the next thing to do is to obtain the carryover factor, right? So which is a function of the ratio of the induced moment to that of the applied moment. And this would always result to 1 over 2, which is half, right? So this is important because we are going to be applying this in our iteration process. So now next to find is the fixed end moments, right? So this is the fixed end moments for uniform beams, and I have about 4 of them here. As applied to your beam analysis, you might want to search for some other so that you can have the right fixed end moment values for your application, right? So to obtain that straightforward, let's just go through, and you have to be mindful of the uniqueness of each member span, then apply the value appropriately. So for the fixed end moment right now, we have fixed end moment AB, and this place being a simple support, we have, or being simply supported, we have the fixed end moment to be 0, and which will be the same as that of MFDC, that is at this point the fixed end moment to be 0, right? So we have the fixed end moment for span BA. Now, of all these that I've written, these free body diagrams representing beams with their fixed end moments, right? Of all these, we have this to be much more similar to span AB, right? So the fixed moment on BA would be plus WL square over 8, and that's going to be 40 multiplied by the span square over 8. That should give us plus 80 kilonewton meter. This sign convention should be actually monitored. Like I told you in the last session, that the sign convention that I assume to use, of course yours might be different, just ensure that you're consistent in its application, right? So mine on this side anti-clockwise, which is negative, right? And on this side clockwise, which is positive, right? So and that's why we have BA to be positive, right? So the fixed end moment for span BC, right? So of course this is going to be negative, being anti-clockwise, right? For span BC, of all these four fixed end moment diagrams that we have this to be representing that, seeing that this the assumption for our fixed for our moment distribution says that all our joints are rigid, so they're more like fixed, right? So this BC is an interior span which has its supports and joint fixed, right? So that makes us select this appropriately to be minus WL square over 12. That's minus 30 multiplied by 6 squared over 12. This should give us minus 90 kilonewton meter, right? So for the span BC still, but now the fixed moment CB, right? That will be positive. If this is negative here, this will be positive, right? Then this also going this way will be negative. Just that application, right? So we have WL square over 12 still. So it has the same value as this previous one, but in the opposite direction. Then we have the last one, fixed end moment for span CD, right? So that would be the same as we had for span AB, right? Which would be WL square over 8. But this time will be negative, right? Of course, we understand why. WL square over 8, and that will give minus 200 kilonewton meter. Now that we have obtained the fixed end moment for the beam, which will be important and needful in the analysis all through, we need to just go forward now. And we have our iteration table, which we'll be using for the moment distribution. So, but before then, we can actually go to find a distribution factor, and we'll be back here. So for this, we can just find our stiffness before this distribution factor. And I told us that to find the stiffness, you have to understand the uniqueness of your span. Then from there, you pick the right formula to use. So for the stiffness for span AB now, the stiffness for AB, seeing that this support is simple, like simply supported, and according to what I told you in the last session, if you do not grab or you might have forgotten, you can check what I explained about the stiffness in the last session. So this would obtain 3EI over L, right, which will give us 3EI over 4, right? And for stiffness BC, and this span such that this is fixed and this also is fixed, yes, so that will be 4EI over L, right? So that would be 4EI over 6. Then for span CD, we have that to be same as span AB, so that will be 3EI over L, which is 3EI over 8, right? So we can have uniformity in our values such that our values will be real numbers or whole numbers rather, and we'll take our EI to be constant. So if our EI is constant, we want to see a way where all our results will be whole numbers void of EI. So to obtain that, we'll have to find a common fraction that can work all through the values we have for our stiffnesses. Then we'll have the whole number. So in my analysis, I've obtained that 24, multiplying all my stiffness results by 24 over EI would help me get a real number. So if I multiply this, I have 18. If I multiply this by 24 over E high, I have 16. If I multiply this by 24 over E high, I also have 9. Right, so these are to obtain the stiffness, and yours might be different basically because of the uniqueness of your beam arrangement. So you should not just find this and stick to it. No, you have to understand what's peculiar to the beam you are designing, then apply appropriately the stiffness factors. Right now, straight up, we have the distribution factors. And for the distribution factors, like I explained in the previous session, for distribution factor BA, right, that will be the stiffness BA, a ratio of stiffness BA to the summation of the stiffness at B, right? So that's very simple. And when you're talking about the stiffness at B, you are talking about stiffness BA, BA and stiffness BC, right? So those are the stiffness at B. And the stiffness at C will be CB, KCB, and KCD. That's simple enough, right? So we have KBA to be 18. Then the summation of stiffness at B will be 18 plus 16, right? That's KBA, which is the same thing as KAB, plus KBC, right? So we have 0.529, right? So the distribution factor for BC will be stiffness BC divided by the summation of stiffness at B still. So that will be 16 over 18 plus 16. And that automatically will give 0.471. There is something that would make you understand that you have done the correct stuff. It's just that the summation of your stiffness across or at any joint should be equals to 1. So, and that's how we have this value, right? So going forward now, the distribution factor of CB will be stiffness of CB divided by the summation of stiffness at C. So that automatically would give us 16 divided by 16 plus 9, right? So that will give 0.64. So the distribution factor of CD now, all right, of CD will be KCD multiplied by the stiffness at C, right? So that would be 9 divided by 16 plus 9. So we have 0.36, right? In addition, you discover that we have a value of 1. Now that we have obtained all these values, we can now return to our iteration table where we'll be able to have the moment distribution. Then we'll be through with it in a very simple and quick way, right? So we can actually have our support as we have been having A, B, C, D, right? So this will be member AB, member BA, member BC, member CB, member CD, and member DC, right? So quickly we have to input our distribution factor as obtained in the previous slide. So we have 0.529, we have 0.471, we have 0.64, we have 0.36, right? So those are the distribution factors obtained in the previous slide. And also the fixed end moment as obtained, we have plus 80 kilonewton meter, right? We have minus 90 kilonewton meter, we have plus 90 kilonewton meter, we have minus 200 kilonewton meter, right? And you discover that there is an unbalanced moment somewhere around there, because these fixed moments, they are practically not balanced, so we need to look into them and create a balance before we can proceed. So we have plus 80 minus 90, that will give us minus 10. So that's the unbalanced or out of balance moment that we have here, right? Plus 90 minus 200 will give minus 110. That's the unbalanced or out of balance moment that we have here. Now, to obtain the balanced moment for these supports, we have to multiply the out of balance moment by our respective distribution factors, right? So we have this out of balance, which is minus 10. We multiply by the distribution factor for BA, and doing that we would have a value. And each time, please note, each time you multiply your moment by the distribution factor, your sign convention changes. So minus 10 multiplied by 0.529 will have positive 5.29. Please do not forget. And here you have also multiplying minus 10 by 0.471, you have plus 4.71. That's simple. Now multiplying minus 110 by 0.64, you have plus 70.4. Then this also multiplying minus 110 multiplied by 0.36, you have plus 39.6. Right, simple. Now for the carryover, it is such that you have to use the ratio obtained in our previous session, like I told you, that we obtain 1 over 2. So you have to divide each of your values by half or 0.5. You multiply by 0.5 or you divide by 2. So having to divide 4.71 by 2 or multiplying by half as obtained, you'd have 2 point you have 2.355, right? So you're carrying over from this support down to the other support. We do the same for this also, and we're going to have plus, this one's also plus, so we have plus 35.2. That's simply dividing these values by 2, right? So we move ahead to balance or to distribute these respective values. So distributing these values just as the way we've been doing, multiplying 35.2 by 0.529 here would have minus 18.621. And you know why it is negative? Because we multiply by the distribution factor, which in turns would change your sign convention, right? So multiplying 35.2 by 0.471, which is the distribution factor here, you'd have negative 16.579. Yes. So multiplying 2.355 by 0.64, you'd have also negative 1.507. Multiplying this same value by 0.36, 2.355 by 0.36, you have negative 0.848. For the carryover factor, just the same way that I've told you now, is to just divide what you have here by 2, then carry over to the other support. You do the same for the other value, then you're gone. Now for this also we have a value of minus 8.29. That's dividing by 2. And this also you divide by 2, you have minus 0.754, right? So what you do now is to distribute also by multiplying those values by distribution factor, then you have distributed values for your moment. So we have positive 0.399. How do I obtain this? Multiplying your carrying factor by 0.529 up here, you'd have this. Multiplying that same value by 0.471, 0.759 multiplied by 0.471, you'd have positive 0.30 or 355, right? 0.355. Let me just clean this off. 0.355. So straightforward now would have this distribution also. 8.29 multiplied by 0.64, you should have positive 5.306, right? So multiplying minus 8.29 by 0.36, you should have positive 2.984, right? So this is simple enough. So what to do now is to sum to find the total of all our moments and see if we have a balanced final moment, and that's going to be our support moment for this beam, right? So you just find the addition right from there down to this place without this value. So do not make that mistake. Without this value, so don't add this out of balance. You know, this out of balance exactly it was the one we tried to find a balance out from. So do not apply this in your addition. Just find a way to add all through your moments without the out of balance moment, right? So doing that simply should give us a final moment, which, if well done, should give these values. Adding all through here should give you okay, let's use a brighter one. You should have 64.262, which is a positive one. Then adding all through here without the out of balance moment, like I said, you have the positive negative actually 64.262. Right, on this other end you do the same, adding all through to this point, you'll have positive 158.392. On the other end you do the same, 158.392. So simply this is how we obtain our support moments for statically indeterminate structures using moment distribution method, right? So if you have further questions and any other issues around this, you can reach out to me through the mentorship platform, or you get to me through the email, and I'll be sure to give you a response as soon as possible. See you in the next module. Bye.